Hello everyone, I'm Anqi. I'm here to present our paper on structured composable policy class for robot learning. In most of the existing work on learning robot policies, fully connected neural networks are often used to parameterize the mapping from state to action, namely the policy. On one hand, these fully connected neural networks are powerful because they are universal function approximators. However, this also means that they're extremely inefficient. Therefore, in order to make robot learning practical, an essential step that we need to take is to find a policy class which can encode structure in robotics problems. Let's first consider an example where we want a robot manipulator to reach a target without colliding into obstacles in the environment. We can decompose this problem into a few simpler ones, which gives us the notion of subtasks. To solve such multi-objective robotics problem, we choose to look into composable policies that look a lot like Lego blocks. So the key questions here are, first, what does a Lego policy look like? And second, how can we put these Lego policies together? We build on an existing framework called Riemannian motion policies and describe each subtask policy as a desired acceleration policy and an importance weight policy. To combine these policies together, there is an algorithm called RMP2 in the literature. It combines the RMPs using a message passing algorithm on a data structure called the RMP tree. It has been shown that the combined policy from RMP2 is stable as long as each Lego piece policy satisfies certain control Lyapunov condition. Practically, RMP2 has also been applied to a wide range of robotic systems. RMP2 is a powerful vessel for encoding structure in robotics problems. It also has nice theoretical guarantees. However, the RMP2 message passing algorithm is quite complicated. It also requires the user to specify a data structure called the RMP tree, which is usually not a trivial process. In our paper, we propose a new alternative algorithm called RMP². It offers all the benefits that RMP2 has, but it is also a much simpler algorithm with cleaner user interface. It has a smaller memory footprint than RMP2, but more importantly, this new RMP² algorithm can interface with learning very easily. The key observation behind our RMP² algorithm is that RMP2 is essentially solving a weighted least square optimization problem, which has a closed form solution given right here. We further notice that this closed form solution can be efficiently computed using the backpropagation algorithm natively supported by automatic differentiation libraries. Moreover, in those autodiff libraries, a computational graph is automatically constructed as we specify the task maps. So with our new RMP² algorithm, we no longer need to specify the complicated data structure, nor do we need to implement the message passing algorithm. Instead, we can let the autodiff libraries to do all the heavy lifting. What is more important is that we can now officially consider this RMP² algorithm as a module in autodiff libraries. And we can use this RMP² module, which naturally encodes structure, to parameterize robot policies. As a case study, we consider a reinforcement learning task where we want a Franca robot to reach the green target without colliding into any of the gray obstacles. We're trying two types of policies for this task. The first one is a fully connected neural network. The other is an RMP² policy. We're trying both policies with 500 iterations of PPO. As you can see, the NN policy is still far from being reasonable and still results in collisions with obstacles in the environment, while the RMP² policy managed to achieve the task. If we look at the quantitative results, we can see that the RMP² policy achieves good performance pretty quickly, while the NN policy struggles to improve. Here's a plot for the percentage of safe episodes at each stage of learning. When trained with RMP² policy, the robot never collides into any obstacles throughout learning, meaning that the RMP² policy is always safe. With that, I will conclude my presentation. Thank you all for listening.